Hi, folks. So my name's Tom. I'm just going to be chatting a little bit about what is eTES, electric thermal energy storage. Um, so the the fundamentals. If you have any material, pretty much any material, with a low vapor pressure, so that's something that doesn't boil, so water is out, you can store huge amounts of energy just by heating it up to a high temperature. So this could be like dirt to rock level of stuff up to fancy materials. Most things have a pretty decent heat capacity, and you just need to find something that survives high temps without creating a large pressure. There is a trade-off between how cheap your material is and how it performs. So dirt is dirt cheap, but it has dirt performance, and that is going to have cost implications for how your system is integrated and footprint and all of your ancillary costs. Why would we do this? Well, first of all, storing heat is a lot cheaper than storing electricity, for instance, or chemical energy. It is also a lot more efficient. So we can simply store more for less money. That's nice. Okay, why would we store in the first place? And Ian has alluded to this already. Basically, we're at the point where if you directly electrify baseload electricity is going to cost more than fossil fuels in many circumstances. Being able to buy just in the off-peak gets you significantly cheaper electricity to the point where it's competitive with fossils. That's why we're doing this. So what is Rondo's version? So I'll just stop for a second and show you, do a little bit of a show and tell. So, oops, a bit blurry. That's a sample of our brick. It's a lumen silicate brick. It's used in electric kilns or any kind of kiln, basically, as just a interface. It's tough and cheap. That's some of our heater wire. It's iron with a little bit of aluminium in it, so you get a nice oxide coating and it doesn't degrade at high temps. Okay, so we have a bunch of bricks. They're not tiny bricks like that. They're actually quite large. We have a bunch of bricks in a stack with resistors, and we are taking electricity into those resistors. It can be from the grid. It can be, we have projects where we're building completely off-grid systems, and we have systems that are only connected to the grid and buying electricity from far away. And we have combinations where people have a generator located close by, but they're also using the grid to supplement. So we're charging flexibly based on the resource or based on prices, storing a large amount of heat, and then we have a second control system that is blowing air through that stack of bricks to deliver heat to the specifications that the customer needs, so their SCADA system can communicate with ours and demand basically like a steam, pressure, temperature, flow rate, that kind of stuff. It's 95% plus efficient, very good. That's pretty much, I mean, not other kinds of storage are just not going to get close to that. So here's a couple of, like a 3-day example of how you might see a heat battery operating. So this is our small unit. It's delivering 7 megawatts of thermal energy on a continuous basis, and it's charging up to 20 megawatts electric, just when prices are cheap. So you can do that quite flexibly. You don't have to do it in big blocks, but it just happens that's how the pricing was. And you can see while we are charging, the state of charge of the battery is increasing rapidly, and then when we're not charging it, it declines slowly until we have to charge all over again. Worth pointing out, we're charging and discharging at the same time. That's a trick a regular battery can't do. What is Rondo up to around the world? So Australia is our newest region. Elsewhere in the world, we have 2 projects under construction. We have a demo project that's been in operation for a bit over a year. And we're going to start construction on a few new projects, primarily in Europe, and more of them are in execution phase. And we have a partnership with a Thai company called SEG. They have a ceramic subsidiary, and they're the producer of our bricks. We can produce 2.4 gigawatt hours per annum, and I think we're at about a third capacity or something like that at the moment. So why are we in Australia? Basically, the wholesale prices are good. You can get access to them as a large consumer, and it's pretty remarkable how good they are relative to the cost of gas. Okay, so Victoria, I've kind of chosen a good example. It proves the point. It's not as good as this everywhere. This is a distribution of price from lowest to highest across an entire financial year. So I've put the graph, otherwise we can't see anything. Price can go as low as negative 1,000, but it doesn't do that very often. And it can go as high as 16,000 or over 16,000. That keeps increasing. So there is quite a lot of volatility. I've got negative price 20% of the time. The average without network costs is about the same as gas and carbon. So once you factor in all of those extra costs, it kind of doesn't make sense. This is one of the best states and a good year for price. So 24/7 purchasing doesn't quite make sense. Okay, but what if you don't do 24/7 purchasing? So we ran a dispatch model across this data with the constraints of how the battery would operate. And we can get a average dispatch price across the year of $1 a megawatt hour. In gas terms, that's like, I mean, it's practically free. So it's silly to say, hey, it's 50 times cheaper than gas. It's just very low. If you reduce the utilization of that heat battery just a small amount, you can actually get to a negative number. So I think Ian mentioned this as well. If you're prepared to keep your gas or LPG backup, run it a few days a year, you can get to a net cost of zero operating cost, which is pretty remarkable. When we're looking at the other states on the East Coast, SA and Vic are by far the best in terms of the off-peak price. There is a big separation between the north and the south. Queensland, New South Wales are a lot more expensive. New South Wales, definitely the worst in terms of off-peak prices, although it is getting better. That probably has the most development for new renewable assets that are going to push that down, whereas not that much happening in South Australia, for instance. Tasmania is quite flat because of all the hydro. They already have flexibility, so they don't need significantly more flexible assets. So just let me dream here for a moment. If we look at, how good is this flexible resource for the network as a whole? So roughly East Coast industrial heat demand is about 10 gigawatts if you electrified everything. If you ran that off a heat battery, that's going to be something like 30 gigawatts of flexible load, which is bigger than all of the dispatchable generation sources in the ISP. And you'd get back a small fraction of that as electricity if you've got some combined heat and power in the mix there, which would be nice to have. What does that change in terms of the equilibrium of these resources? Well, we're absorbing more of that curtailed energy, so there's a more profitable equilibrium for renewables. You can build a bit more of them, and that means you don't need to store quite as much energy, so we're getting other capital savings in the rest of the system. And you get other nice stuff like regional development. It makes sense to locate these, for instance, in renewable energy zones, and value add on things like minerals and agriculture, which we're good at, but don't really value add. Thanks.